All right, so we're going to go over some of the experimental background and data analysis for the potentiometric titration lab. Right, so the main goal of this lab is to determine a acid dissociation constant for a monoprotic weak acid. Right, so the acid dissociation equilibrium given here by way of a monoprotic acid dissociating water to get us a hydronium, and then the conjugate base anion. Right. So how we're going to do this, or data we're going to collect, is I'm going to scroll over here to this graph. We're going to record pH as we titrate hydroxide into our monoprotic weak acid. So we'll have a beaker that contains 20 milliliters of your monoprotic weak acid solution, and we're just going to add small portions of sodium hydroxide from a burette into that beaker and record the pH as we go. Right? The sort of idea here is that somehow this information is going to allow us to figure out this Ka. Right? So we got to spend some time talking about, well, okay, what's going on in this graph? Why is that going on, right? If you add sodium hydroxide, right? Sodium hydroxide is a strong base. The pH should go up to your solution, right? And it does, as you look here. So here we have volume of hydroxide added. Here we have pH. As I add hydroxide, the pH is going up, right? But it's not going up very drastically, right? For a pretty good portion, right? Like this sort of portion here, the pH is going up, but not by a lot, right? And we can think about why this is happening. It's just an application of Le Chatelier's principle. If you add sodium hydroxide, right? If I add hydroxide to a solution containing this equilibrium, well, these two are going to react together to give me water molecules. Right? So our hydronium ion concentration is going to go down, which then means the pH will go up, right? But what happens is if I remove some of the hydronium, then my equilibrium is going to shift to reestablish, right? So some of the protonated acid is going to become deprotonated, right? Eventually, though, as I continue to do this and I continue to convert more and more of this into hydronium, there reaches a point where I start to run out of the weak protonated acid, right? That's this portion of the graph, right? So as I run out of this, it should make sense that we start seeing bigger jumps in pH for small additions of sodium hydroxide, right? If I'm starting to run out of this, any hydroxide I add is reacting with the hydronium ion and it's not getting replenished, right? Or it's not getting replenished as much. And so what we're looking for is the point where this isn't getting replenished because I've run out of this. That point's going to be somewhere in this graph around here, right? And we call that the equivalence point. So this is the equivalence point. It is where our protonated acid is stoichiometrically equivalent to the hydroxide that we've added at that point. So the moles of HA that we started with are the same as the moles of OH that we've added at that point, right? We've run out of our protonated form. It is equivalent to the amount of hydroxide that we've added at that point. All right. Okay, so if I've run out of this, that means I have at the equivalence point all deprotonated. So I'm just going to express these in terms of percentages, right? If I have no HA, that means all of my acid is in the deprotonated form, and that would mean that all of my protonated acid, well, there's none of it, right? Because it has all reacted with the sodium hydroxide, right? So that's at the equivalence point. Okay, well, why do we care about that, and how's that going to help us back to our original goal of finding the Ka? Well, if we have a weak acid, right, our value for Ka is really, 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 really small, right? Weak acids don't dissociate very much. That means I have a lot of protonated and not very much deprotonated. And so what we're going to assume is at the start, so at the start, before we add any hydroxide, we're going to assume that all of our acid is in the protonated form, and none of it is in the deprotonated form. The idea here is that because it's a weak acid, Ka will be so small that this assumption is probably a fair one to make considering the equipment that we're using. If this sort of assumption leads to an error that's smaller than something that we can measure, then it's probably a pretty fair assumption to make, right? But at the start of the titration, so here, right? So at this start, I have all protonated weak acid and no deprotonated. And then at the equivalence point, I have all deprotonated, right, and no protonated. Well, again, how does that really help us, right? We got to figure out this Ka value. Well, halfway between our start and our end, if here I have 100% protonated and 0 deprotonated, and then at the end I have the opposite, halfway between, I should have the same concentration of both. So this is called the half equivalence point. And it's literally just halfway from start to end, start to equivalence point, right? Well, okay, cool. At the half equivalence point, these are going to be numerically the same, right? And that means that, oh, hey, look, in this Ka expression, those two numbers are going to cancel out, right? Which means at the half equivalence point, if you know the hydronium ion concentration, that is numerically the same as the Ka value for your acid, for your monoprotic acid. And conveniently, we will. Like, look, we're measuring the pH as we do this titration, right? So you'll know the pH at this data point here, which means you know the hydronium ion concentration, which means you also know the Ka for your monoprotic weak acid, right? Okay, so to sort of quick summarize, we need to find the equivalence point. That's where our change in pH, we have a big change in pH over a small change in volume, right? And we're looking for that because that's where we run out of this and it's all the deprotonated form. And the reason we're looking for the biggest change in pH is to the smallest change in volume is, well, we're looking for where we run out of hydronium that's being replenished by our HA. Right? There's obviously still hydronium in solution, but we get a big pH change because it's not being replenished by our protonated acids. Right? All right, so, well, if we look at this, this is what I'm saying is the equivalence point. We have change in pH over change in volume. pH is the y-axis and volume is the x, right? So we're looking for change in y over change in x. Or what we're looking for is where the slope is the biggest, right? So you have to create two graphs for this experiment. This titration curve that I've already sort of shown here. And to help us find the equivalence point, we're going to plot the first derivative of that graph, right? Because the derivative gives you the slope of the line at any point. And so, well, hey, we're trying to find the point with the biggest slope so that we can find our Ka. So we should plot the first derivative. It'll help us find it. Sorry, I'm just kind of cleaning this stuff up here really quick. All right, so we have, I'm going to zoom into the Excel data part now. All right, Okay. So, like I said, this is just some data collected by a student. They just have their burette readings here, and then the pH that went along with them. So they started their titration at 6.36 milliliters. So to figure out how much volume they added, all I did was I took their burette readings and subtracted the initial reading of 6.36 from all of these cells, right? And then I plotted that data against the pH, right? But again, we're looking for where the slope is biggest, right? That'll tell us where our equivalence point on our graph is. So I need to make that graph, right? I need to plot the slope of this line, the change in pH over the change in volume, right? Well, how do I calculate slope? Well, okay, it's rise over run. So this is going to equal to my rise, which is this y value minus the y value before it. So that's my change in y divided by my change in x, which is this x value minus the one before it, right? I have to put parentheses in here, right? Order of operations. If I don't, it's going to divide the C2 and the B3 first. So put the parentheses around your y values and your x values, right? But this is now the slope between these 2 points, right? It's whatever this difference is divided by this difference, right? And then if we're trying to find the slope between 2 points, right? Well, where do you plot that slope? Well, between the 2 points, right? So I don't want to plot my slope at this point or that point. I want to plot it between them. So what we're going to do is we're going to calculate the midpoint, right? So I can add these two together and divide by 2 to get the midpoint in the x value, right? Right. So this is going to equal to that plus the first point and then halved, right? So 0.47 is halfway between 0 and 0.94, right? And then I'm just going to copy, I'm going to select these two. So I have my midpoints calculated and I have my slope calculated, right? I'm just going to drag these down through all my data points. So you'll notice I get kind of weird answers here for the last two, right? By doing a subtraction and a midpoint, you inherently lose one data point, right? So I'm selecting it just to show you C103, which is not where I have data, right? So I want to ignore this one. I'm just going to delete it, right? But then select through your data, go to insert, make a chart, boom. All right, I'm going to zoom out a little bit. All right. Did not mean to do that. So here we have our first derivative. I'm trying to kind of line up the axes a little bit so you can sort of hopefully make sense of this, right? Okay. So, right, initially, like I said, our slope is pretty small, but it reaches a point where we start running out of our protonated acid, so our pH starts changing more drastically as we add hydroxide, right? And then once we get past that equivalence point, linear additions of hydroxide will sort of cause the pH here to flatten out, right? But this is it. This is our first derivative plot, and so what I'm looking for is the point where the slope is the greatest, right? This is the slope. I'm plotting the slope as my y-axis, and this is still the volume of hydroxide added. So my equivalence point, if I hover over that highest point, is 26.135 milliliters, right? So half of that is 23.07, or sorry, half of 26.14 is 13.07, right? So my half equivalence point is at 13.07 milliliters, right? So I'm going to go back through my data here and try to find one that's close to that. All right, so I don't have a data point for it, right? But 13.07 or is sort of between these two, right? So I'm just going to say this is close enough, right? So at my half equivalence point, which I'm going to highlight here in yellow, right? So at my half equivalence point, my pH is 5.060, right? So that pH tells me the hydronium ion concentration, right? Or you can figure out the hydronium ion concentration from that. And therefore, you can figure out the Ka from that. Because at our half equivalence point, the HA concentration is numerically the same as the A minus concentration, so they'll cancel out in the Ka expression. Right. All right, that is all that I've got. Thank you for watching. Have a good one.